Hello. So today I want to talk about the equations of simple harmonic motion. And there are quite a lot of equations of simple harmonic motion, but before we get into it, I would strongly suggest watching my previous video on what simple harmonic motion was in general, where I talked about pendulums, the requirements, and what things basically showed simple harmonic motion, as well as how they moved in general. So I strongly suggest watching that video before you watch this one. Equations of simple harmonic motion. First thing we need to get out of the way is how we can represent this. So when we have a circle, and let's say we're looking at this like little point that's moving around in a circle constantly, we're looking at 2D motion. Let's say we rotate this circle so that we can only see a line of it, right? But you can still see the point moving around the circle, which will now look like just it's moving up, a bit slower on the top and then a bit faster here, and then it's going down a bit slower here and then a bit faster here. Why is it a bit faster in the middle? It's because when you're moving like here, you can see that it's actually moving. When it's moving across the top, for you, this is all going to be kind of like stuck together, as this part would be like just seen like this, right? So although it moves through a long point, it's just gonna look like a short distance to you. So it's gonna look like it's moving a little slower. So yeah, that's how it would work. And this is the exact same motion as an object in simple harmonic motion. So what we basically conclude is that we can represent a simple harmonic motion oscillation because it's literally the same as if you took a point that was going around in a circle and then you made it 1D and you looked at its motion, which means to say that it moves through 360 degrees in every oscillation. So a complete oscillation has 360 degrees, or it's 2 pi radians per oscillation. And it's much better to use radians in this case. And then we have frequency is how many oscillations are made per unit time. So for example, if a certain object is moving, this object for instance, and then it's moving at 3 hertz, which means it's having 3 oscillations per second. So it's going 1, 2, and 3 every single second. This is going to be 1, 2, and 3 every single second. So now that we know that, we want to find the angular velocity. Angular velocity is how much in angles an object travels through per second. If this some object travels through 3 hertz per second, it means that it's going through 3 circles. That is 3 times 2 pi radians. So 6 pi radians per second is the angular velocity. Now that we've gotten that, it's very easy to see that the angular velocity is very simply just frequency of a simple harmonic motion object times 2 pi radians. That's where we get this first equation from. So we know that the omega equals 2 pi frequency, and then we can also talk about how the frequency is the reciprocal of the period, t. So we know that frequency is omega divided by 2 pi. If we switch this around, we're going to get t, which gives us this equation. If we switch these two, then we're going to get this equation. So these are just very, very easy to derive equations. This is the one that is more important. And where do we get this? We're going to get it by looking at the motion of a circle and flipping it a little so that it just looks like a line to us, and realizing that their motion is the same thing. So the second motion, and possibly the most important equation of all time, is that x, which is the displacement, is xo, which is the maximum displacement or amplitude, sine omega t. And we're going to derive now this specific equation. So let's start with this. Let's say this is a mass, and it's probably a metal block, and it's currently at rest right now. It's connected to a wall by this spring, which is zero tension, it's just there. And then we decide to give it tension. We decide to displace it to one side and let it go. because the spring has been stretched, it's going to contract, and then because the spring has been contracted, it's going to push out again, and then, you know, it's going to keep on going about this motion. This mass is going to start oscillating between a central point that we know as the equilibrium position. And therefore, this mass is going to go into simple harmonic motion. So we can use this. I'm pretty sure we all know that k is F divided by x. So F is, this is the k is the spring constant, right? So F is going to be kx, but in our very specific case, we're going to put a negative sign here. Why? Because, for example, if we decide to stretch this here so that this spring gets like stretched out and then the mass is over here, although the displacement is positive, we know that the right side is conventionally positive, left side is conventionally negative. Although displacement is positive, the force is going to be towards the negative position in the opposite direction, because this is stretched, now it wants to go back. So basically, that's why we have this negative sign over here. It's a bit different from, you know, when you put a load onto a spring and then you try to measure all these things. So that's our first equation. We also know that F equals ma. Which is our second equation. We can equate these two together. So we would get minus kx equals to ma. A equals to minus kx divided by m. Now we know that a is going to be d squared x divided by dt squared. If you differentiate x with respect to the time, and you differentiate it once, you get the velocity, the rate of change of displacement per time. If you differentiate it one more time, you're going to get the acceleration. So that's why I've put this differential equation over here. And we can put this thing over here. We get kx divided by m equals 0. So now we just have to fill in the gap. Which equation can we put as x so that when you differentiate it twice, you're going to get the negative version of the exact same equation so that it cancels out and it becomes 0? Well, we know that the sine function would do it. If we have x equals sine theta, dx dt is going to be cosine theta. D square x out of dt square is going to be negative sine theta. So if you add x with its double differentiated version, you're basically going to get 0. This is how we know that x is going to be in a sine function. Now we have this omega thing, and we're just going to put this whole entire equation inside. So let's say we just differentiate this twice for a second. Let's differentiate this twice. So the first time we differentiate it is going to be the amplitude times the omega times cosine omega t. Second time we differentiate it is going to be the amplitude times omega times negative sine omega t. So let's just delete all of this and start over again. We finally have d square x out of dt squared is negative omega squared amplitude sine omega t. So our previous equation that we had before I deleted everything was this. That was our equation. So we can now substitute this. We have basically used the equation that x was the amplitude or the maximum displacement of the motion, sine omega t, right? So if we put these inside, we're going to get negative and then you're going to get plus km divided by m times xo sine omega t, which is going to equal 0. So if you rearrange it, you're finally going to be left with the equation that omega squared equals k divided by m, which is actually true, as you will see in the later videos. But this is basically how they derived that the equation for x is the maximum displacement or the amplitude. If you had been shown a graph and it was like this for an oscillation, the maximum displacement is going to be the height of a crest or the depth of a trough. It's going to be that sine omega t, omega being the angular velocity, and make sure that the angular velocity is in radians per second. So yeah, that's basically how they derived it. We can also state that x equals, amplitude cosine omega t, because it's the exact same thing. It's just going to be like this. It's just going to start at a different position. But conventionally, we would use this, and this is how we derived all of it. Now we're presented with a new equation, and that is a is equal to negative omega squared divided by x. And let's just ignore that for a second. An object's acceleration in simple harmonic motion is directly proportional to the displacement. What does that mean? It means that when, let's say, there is a pendulum, this is the equilibrium position, the bigger the displacement x is, the bigger the acceleration will be. It also tells us that the bigger the displacement x is, the bigger the force, the restoring force F would be, because F equals ma. So that's something that we can observe. And the constant of proportionality is negative omega squared. So because, acceleration is directly proportional to x, a is negative omega squared x, the constant of proportionality is going to be that. Now, how can we prove it? Well, in the previous equation that we just came up with, we finally concluded that omega squared equal to k divided by m, if I'm not wrong. Yeah. So we know that k divided by x is ma, right? And that's because, this is the force. This is also going to give us the force. And k is going to be minus x ma. Remember that, it was k is minus x times f for that specific equation. So we can, substitute this into this. We're going to get omega squared equals to minus x a divided by, oh no, the m is going to be gone. Yeah, and then we could, we would get minus xa divided by m. Oh, hold on, sorry. This is going to be ma divided by x, minus ma divided by x. So if we substitute it inside, we're going to get omega squared equals minus ma divided by x times 1 out of m. We can cross these off, and then we're going to get a is negative x omega squared. And then we can show this equation from the previous thing that we did. So yeah, that's how we get that equation. Equation number 3. Now then we have the stiffer a certain spring that we might have used last time, the higher the force for a given displacement. Because if you have a very, 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 very stiff spring and you stretch it out for a displacement x, you need to put in so much force than you would if you had like a looser spring for the exact same displacement. That's why the stiffer the spring, the higher the force for a given displacement. And hence it gives faster acceleration or higher acceleration, and hence the frequency would also be higher. If you have a higher acceleration, you would also have a higher frequency. So the equation that we just derived, a is negative omega squared x, is a definition of simple harmonic motion, which means that the equation must be fulfilled for a body to be in simple harmonic motion. So a body executes simple harmonic motion if its acceleration is directly proportional to its displacement and in the opposite direction to its displacement. We can get that very, very easily from this simple equation. The acceleration is in opposite directions, which we have the minus here. It's in it's directly proportional to its displacement. The higher the x becomes, the higher the magnitude of the acceleration would become. So if we were to graph acceleration of the simple harmonic motion object and the displacement of it, then we would get a graph like this. So we would have a straight line graph passing through the origin. It's not perfect, but it is passing through the origin. And we can see its characteristics right here. It's a straight line through the origin. That's because the acceleration is directly proportional to the displacement. It has a negative gradient. It's because of the negative omega squared, the fact that it's going to be in the opposite direction to its displacement. And also the gradient is independent of the amplitude. What does that mean? Well, let's say this is the amplitude, xo and minus xo. Even if the amplitude was much smaller, let's say the graph ended here because the amplitude was so small, and it was much smaller, that was here, and this was reduced to here, the gradient of this graph will still be the same. What does this tell us? Well, this tells us that the frequency of the motion is basically going to be also independent of the amplitude of the motion. The period taken is also going to be independent of the amplitude of the motion. And how do we know this? Well, we know this probably because the acceleration would be defined by how much the frequency is. So yeah, that's what we can tell from these equations that we've derived. On the other hand, x equals xo, which means the maximum displacement, sine omega t, is actually a solution to simple harmonic motion. It's not a definition. It tells us the value of x with regards to t. And actually, we can do even more proving, where we can actually prove another equation. So let me show you. So we have this equation, x is xo sine omega t, and then we have the equation acceleration is negative omega squared displacement. So those are the two big equations that we've gotten. We know that if you differentiate this twice, you're supposed to get acceleration. Let's differentiate it once. We're going to get velocity, right? That's going to give us xo omega cosine omega t. Let's differentiate this twice. We're going to get xo omega squared and then negative sine omega t, in which case we will get negative omega squared xo sine omega t. Now we know that x is xo sine omega t. We see xo sine omega t right here. So we're going to substitute this into this, which basically will give us a equals negative omega squared x. That's how we can also prove that this equation holds true from this equation. Now, as I've just shown you with my previous differentiation, the velocity can be represented by this because you differentiate it once, you differentiate x with respect to the time, right? You have, sine omega t, you can differentiate it once, and then you're going to get this equation. So if you differentiate it once, you get this equation. We know that the maximum velocity of an object in simple harmonic motion is going to be when it passes through the equilibrium position, right? Which means x is going to have to be the highest. Oh wait, no, this is not it. The x is going to be 0, right? But x is not in this equation. The velocity is going to be the highest, or the maximum velocity, when t equals 0. So when t equals 0, the velocity is going to be the highest. This is for a standard sine graph motion, for example, like this. If this is the displacement, you're going to pass through the equilibrium position when the time equals to 0. So that's what we have. Now, cosine 0 is 1. So let's say the maximum velocity is VO. VO is going to be negative omega the maximum velocity, the maximum displacement times 1. So that's what we've been able to prove. Now we substitute this back into this equation, and that's when we are going to get this equation right here. So because we have omega and then the maximum velocity, and we know that this is that, we can say this is actually, no, this is just VO. And that's where we get the equation V equals to the maximum velocity, which is also the velocity you're going to get when you're moving through equilibrium position, times cosine omega time. So that is another important equation. And then we have finally this equation, which I think you should just memorize because it is not specified yet. So yeah, we have these two very important equations. The velocity or the speed can also be represented by plus minus, depending on the direction that's going to, omega and then the maximum displacement squared divided by the current displacement squared. So those are the two more equations. Okay, so this is the final bit. The maximum speed means that the object is at the equilibrium position. So that means that the displacement from the equilibrium position is obviously going to be 0. So using the previous equation that we got, which is plus minus omega is going to be square root this, we know that at the maximum velocity, which is VO, this is going to be 0, which means it's going to be plus minus omega x squared minus 0, which basically just leaves us with omega squared, which basically leaves us with VO is omega x. Oh, sorry, forgot to put a 0 here. This means that's the maximum displacement. So you can actually even get the speed of something, the maximum speed of something, by just knowing the angular velocity as well as the maximum displacement. So we get this equation at the very end. V is going to be omega x 0. This also shows that V is proportional to omega. V is also directly proportional to the maximum displacement. Sorry, not velocity, maximum displacement. Now, how can I explain both of these things? Well, V is proportional to angular velocity because if something is moving around at a faster speed inside the circle, it's obviously when you translate it into an oscillation going up and down for the exact same length, let's say, it's going to be moving at a faster velocity at its middle point, right? And that's how we can explain that. V is also proportional to maximum velocity, so this maximum displacement. So let's say instead of this small oscillation, there's a bigger oscillation. This is going to be that the velocity at the very central point, the maximum velocity, is going to be much higher than the one here. Why? Because it's accelerating up till the point that it reaches its middle point, and then it starts to decelerate, right? That's how simple harmonic motion works. It accelerates when it's moving towards the middle point, and then it starts decelerating. If you have more distance between the end and also the point that you're accelerating towards, then you're obviously going to be able to do even more acceleration, achieve more acceleration throughout this period. And that's why we can prove that V is also directly proportional to the maximum displacement. And do remember that by V, I mean that maximum velocity. It's very important not to forget this. So that was a pretty long part, and that's why I put a little summary here. So we have a summary of every single equation that we've come up with. This is the first one that we got by making the circle into the oscillating thing. This is the one that we got where we can basically give the solution to simple harmonic motion, the sine one. From this, we can get the cosine one, obviously, and then from the and then we can also, from this, get this as well. We've been able to prove that as well. We've also gotten this equation, and from this equation, this alternative equation for the velocity, we've been able to get that the maximum velocity is going to be omega x maximum displacement, right? And we have also explained why the maximum velocity is going to be directly proportional to both of these constants. So I hope you're able to probably memorize these because the derivations make sense, but they're a bit hefty to derive all of them during exams. And I just wanted to talk about how they got there in the first place. In my next video, I'm going to talk about energy changes in simple harmonic motion, damping of simple harmonic motion, and how resonance works and the uses of resonance, and they're all coming up, so keep updated for that. And thank you so much for watching.